with talking about the comparison test today, and later on we'll talk about the limit comparison test. Here's just some examples of some series that we've seen up to this point. So I've got these series here in brown and these series here in blue. And these brown ones, these are all geometric or power series. So my geometric looks like just one thing raised to the nth power. So the base, what I want you to notice is that the base stays the same, but the powers are the thing that increase from term to term to term to term. So here I've got 2/3 as my base in every single term, and my power is the thing that's increasing. And now this one is a power series because it's my x to the n that's increasing, right? But then I also have this a sub n. So remember, your power series looks like your geometric, but with another sequence multiplying each term. So you have another sequence out there. So I've got these powers of -1, and we're actually not going to deal with alternating series. So we can cross this one out. So today we're only going to look at series with non-negative terms. So in all these ones in blue, these are all the p series. So these are all p series. And basically what we're going to do is we're going to look at these, and these are kind of like the bases for what we're going to do. What if I had something more complicated? So this one's not technically a p series because I have this multiple of 2. I would have to factor that 2 out. This is really the p series 1 over n cubed times 2. So this is a p series, but you really need to remanipulate it so that it actually is a p series. So let me rewrite that. So this is equal to 2 on the outside, and now you can see the p series, right? I've got n, notice here my base is the thing that changes. In my p series, it's the base that changes and the power that stays the same. So here I've got powers of 3, here I've got powers of 1/2, here I have powers of 1. Remember, this is our classic harmonic series. This is the one that we know classically diverges. We're going to look at p series, and what we're going to do is we're going to say, well, what if I take something that looks like a p series, but it's actually more complicated than that? What if I take something that looks like a geometric series, but it's actually more complicated than that? What if I had 2 over n cubed minus n? What about this thing? Does that thing converge, right? I don't know. That's the question that we're going to ask. And that's what we're going to look at as we do our comparison tests. Let's consider the series from n equals 1 up to infinity of 1 over n cubed plus 2n plus 1. Well, it reminds me a lot of the series 1 over n cubed, right? And I feel like most people, if they've dealt with power series to this point, they look at this and they just say, oh yeah, duh, that converges. You could say that, but that doesn't really give you convergence. Like, it's true that this goes to 0. You can easily prove that you can easily prove this. Sure, that's easily proven, but this does not imply convergence. Of the series. Yes, the terms, the sequence converges, but that's not enough to give you series convergence. Remember the harmonic series, right? So here's the really cool idea that we're going to try and do with the comparison test is we're going to say, what does it look like? And can I directly compare it? That is, if this goes to, remember, this converges, right? Well, this p series, classically, this one diverges. Oh, the harmonic series, it diverges. So if I can show that my terms are bigger than term for term something that diverges, well, if this thing doesn't get small enough fast enough, right? If this thing is too big, if the addition of these terms are too big to add up to something that converges, if it diverges, then something even bigger should also diverge. On the other side of that, if these terms are getting small enough, right? If these terms get small enough term for term, then something smaller term for term should also converge. And this is the idea behind the comparison test, is that this does good, and if I can find something term for term that's smaller, then the other one does even better. So here's what we're going to do, is we're going to take a look at this, and we're going to say, hey, it reminded us of this. And I know that this thing converges because it's a P series, and its P is 3, so it's going to converge. And here's the other thing I know. I know that n equals 3 plus 2n plus 1 is going to be smaller than 1 over n cubed. And here I'm going to use some notation. I'm going to use this notation. And this means for much bigger than 1. It's another way of saying for sufficiently large. If I have an n that's sufficiently large, it's true that this thing is going to be big. Now, notice that much bigger than 1 isn't, well, very much bigger in this case. In fact, 1 does the trick. We can see right away that since n cubed plus 2n plus 1 is directly bigger than n cubed, that when I invert it, this thing is going to be smaller than that thing. So the idea being that if this sum converges, right, if these terms are small enough to converge, well, it's got to be the case then that this thing also converges, right, that it converges to something smaller than it. And again, think back to when we were talking about it in terms of area. If this is taking up so little area that its area is finite, this is taking up even less area, and so it's got to also converge. It's a breakdown of what we're going to try and do with the comparison test. So the very first step is to say, what does the series that we're looking at that we don't know, what does it remind us of? Does it remind us of a P series? Does it remind us of the harmonic series? Does it remind us of a geometric series? What does it look like? And then we want to know, is the series, the one that it reminds us of, the known one, is that series convergent or is it divergent? And sometimes you'll take this in a two-step process. You'll say, oh, it looks like this one, but I still don't know about that series, so that series now looks like another series. You're going to kind of go in a process of that sort of thing. And then finally, the last thing that you want to answer is that depending on the answer that you got from here, from 2, if it's convergent, what you need to do is that show each term is, that is, of the unknown series, you need to show that eventually it's smaller than the known series, that the comparison series terms. That means I want it to be smaller than the series before. So I want it to be better than good. The comparison series, its terms were good enough to actually converge so that the series converges to some answer. If my unknown series, if I have smaller terms, that means I'm adding on smaller and smaller things, which means that they're doing better than good, which means that they will also converge. If my answer to 2 was that the known series, the thing I think it looks like, is divergent, then what I want to do is I want to show that each term of my series, the one that I'm curious about, I need to show that it's bigger than the comparison series. And again, I can do eventually. And the reason why eventually is in here is because who cares about the first couple terms, right? We care about infinity. So what I'm trying to look for is I'm trying to look for infinity on these guys. So again, here I want to make sure that my terms are worse. So the thing I'm comparing it to is divergent. That means that these terms are bad they're big enough, they're bad enough that they diverge, and I want to show that my new series, the series that I'm curious about, I want to show that they do even worse, that they're even bigger term for term. Now, what if, Amy, what if I can't do that? What if I can't show that each term is directly smaller for a convergent or directly bigger for a divergent? That's okay. We have other tests. What that means is that this is not the test for you. Move on to the next test. Try the limit comparison. Our example at hand. So what we've shown so far is we've talked about why this thing is less than this thing, and we're talking about the terms. And notice that this is going to be true too, right? That I'm bigger than 0. I'm adding up. So this is why we want to work with non-negative terms. Right? Remember what we showed about series with non-negative terms. They always have a sum, and it's always either finite or infinite. If my series has to have either a finite or an infinite sum, and I know that this series, that the series with this sequence for its terms is finite, and I know that this series has smaller term for term, its sequence is smaller, then it has to be that this thing is finite. Do you see that it would be impossible for these to add up to an infinite sum, and then these things that are bigger than, to add up to a finite sum? So because this is because this is a convergent series, and we have non-negative terms. This is super important. And we have another series with and these are both series with non-negative terms. You are forced to have this also converge, to have also converge. So let's formalize this idea. Is the comparison test laid out formally? So the comparison test says, suppose that you have 0 less than or equal to a sub n, less than or equal to b sub n, for all n greater than or equal to some n. And that just means eventually. So what we're saying is that eventually, and forever after that, we've got series with non-negative terms. That is, we could chunk off the first finite and throw them out and say, hey, we're just curious about the series after that. What's happening with that? If I want to know what the actual sum is, I can then tack back on the finite things that I got rid of. But also, I want to know that these two are comparing in this particular way. So this is giving me not only that they're non-negative terms, but that the terms term for term are in fact comparable. So then what I have is that if b sub n converges, so if this thing converges, then the sum of the a sub n's also converges. So what that's saying is that the series with the larger terms, if those converge, then it's forcing this series here with the smaller terms to also converge. Because remember, what does it mean about to have non-negative terms? It means that your sum has to either be finite or infinite. And we're saying that the sum of these things is finite, and it's forcing the sum of these things to also be finite because we've smushed them together in this way. The other thing that you might get is you might get that the sum of the a sub n's diverge. Now, these won't happen at the same time, obviously. So if the a sub n's diverge, then that forces the sum of the b sub n's to also diverge. So if a sub n is the series that I know and b sub n is the one that I wanted to know about, then when this thing diverges, if I can show direct comparison, that forces the b sub n to diverge. So when I'm using this, if I want to show my series diverges, I need to find something smaller term for term that I know diverges. If I want to show my series converges, then I need to find a series bigger term for term that converges. Now make sure that you're only doing this on the terms. This is absolutely not used for partial sums. You can't use it on the partial sums because this whole thing is hinging on the idea of what we know about non-negative, about series with non-negative terms, right? And so this is not about the partial sums, this is about the sequence of the terms.